Hello everyone, let us start lecture 32. Now, in this case the topic will be anodic protection of metal which is related to active passive metal. And its analysis and I would say mixed potential theory. Actually, we'll try to have reasons on the basis of mixed potential theory why active passive metal can be anodically protected. Now, as we have seen in case of cathodic protection, the theory says, the mixed potential theory says, if you see cathodic protection, so this is E volt and then this is log I ampere per centimeter square. Now, that case we have interacting active metal interaction and with a cathodic reaction. So, this is my I A, this is I C and this becomes I core. So, respective points, we know what are those points. Now, that theory says in case of cathodic protection, once you get a stable E mix corresponding to I core, if you reduce that potential, okay, so if you go downwards, that means we are going this becomes negative or over voltage becomes negative. So, that is what this becomes cathodic over voltage. So, when you let us say from this is the stabilized potential and then if you go downward, then we will see that if you keep the potential at this location, you could see that your cathodic reaction on the metal surface increases because I C would be here, but corresponding I A would be at this location. Now, if we compare I core and I A, we see that I core is greater than I A, or I would say I A is lower than I core, that means the corrosion rate or the dissolution rate as indicated by the anodic current density decreases drastically since this is in log scale. So, this is the cathodic protection. But if I go positive direction, that time situation becomes different. If I go positive direction from the stabilized E core or E mix, I could see that if I go this way, I could see that this line I have to extend and now let us say I have reached this particular potential, and interestingly I see that the I C on this particular metal surface would be here, that means the I C decreases. But if we see I A prime or I C prime, in this particular case where neta is equal to positive or it becomes anodic over voltage, then I core would be much lower than I A. So, that means I A or dissolution rate of the metal increases manifold. Fine. So, that means in case of this active metal, if I go positive side, that means anodic polarization, then I would always increase the corrosion rate or the dissolution rate of the metal. So, no way I can protect that metal. But if I go downwards, if I go cathodic polarization, that is what the cathodic protection name comes in. So, I could see the corrosion rate can reduce from this to this, but if I go positive side, corrosion rate increases from this to this. So, if we follow anodic polarization in case of active metal, I will never be able to protect the metal, rather I would always increase the corrosion rate. But this situation would be different if we follow active passive metal. So, in case of active passive metal, if we draw the active passive metal anodic polarization part, so let me draw that. So, let us say that this is the anodic polarization part, let us say this becomes my E equilibrium of that metal, this is I 0 of that metal in the solution, and let us say hydrogen evolution is the my cathodic reaction. Okay. So, somewhere we have the hydrogen evolution reaction happening at this location, let us say this is the location. Okay. So, this let us say this is the location. Okay. So, now if I see the if I try to see this location. So, now if I draw the cathodic polarization plot, so this becomes my cathodic polarization plot, and let us say this becomes my E equilibrium hydrogen, and this is I 0 hydrogen on that metal surface, and this is of course potential, and this is log I ampere per centimeter square. Let me extend it little more. Now, my natural or steady state corrosion potential is this, and current density corresponding to corrosion rate of that particular metal, active passive metal, is at this location. I can go down for cathodic protection, but if I go up from that E curve, that means if I go anodically, if we follow anodic polarization, let us say I am going this way, okay, and gradually I am moving upward. Okay. If I increase the potential from that E curve, that means the steady state potential. So, I see that if I follow that, I see that gradually I am increasing the corrosion rate, because I A is gradually moving this way. So, finally, it reaches to I critical, which is the maximum current density that is possible in this particular situation. And then once I cross this I critical, let us say potential comes to this location, fine. Now, that time my I A is, let us say this is my I A prime, is located in the passive region. And similarly, if I follow that anodic polarization further, I could see that I A is still, this is I A prime double prime, which is equal to I A prime equal to I passive. So, that means I could see that the corrosion rate is not changing, which is indicated by the anodic current density, because once I take the potential to this particular location, I always have the current density corresponding to the metal dissolution situating in the passive region. Since this particular zone is the passive zone, as per this particular drawing, and below this it is basically active zone. Now, if I can keep the potential at this location, okay. So, if I can keep the potential at this location, that is, let us say this is E prime, double E prime, if I keep E double prime, let us say corresponding to I double prime. So, then I could see that the corrosion rate of the metal would always be as same as the I passive. Now, interestingly, if you see that initially when I go for anodic polarization, corrosion rate increases, reaches maximum at I critical, and if we increase the polarization further, that means anodic polarization, I could see that the corrosion rate becomes I passive. That means the corrosion rate what it was in the steady condition, which is I core, it has gone to the I passive. Okay. So, the corrosion rate has decreased to a great extent, since this is the log scale current density axis. So, this is the very concept of anodic protection. Now, even if we do anodic polarization, instead of increase in corrosion rate as we have seen in case of active metal, which is this incident, here we can experience reduction in corrosion rate, and that is what this is called activation or anodic protection. Anodic protection. Now, interestingly, if I try to see the current requirement at this particular location when the potential is E double prime, I can also find out that let us say this particular current is almost about let us say 10 to the power minus 3, let us say, okay, ampere per centimeter square. Now, at this location let us say the current density is 1. Okay. So, that means it is 10 to the power 0. So, that means this is 1 ampere per centimeter square. Let us say this is 1 ampere per centimeter square. So, that means the current requirement when the at E prime double prime I applied would be equal to I A double prime minus I C. Let us say this particular current density is I C double prime. I C double prime becomes 1 minus 10 to the power minus 3 equal to 1 ampere per centimeter square. Okay. So, this is the current amount you need to pass through that particular circuit in order to have the potential maintained at E double prime, and that time corrosion rate would be same as this becomes I passive 2, because these particular cathodic current density is very low compared to the anodic current density. So, it will be least felt. Now, if I try to achieve the same current density corresponding to if I follow cathodic protection. So, that means from the steady state for E core, if we go down I can reach to this potential. Okay. So, this is let us say E triple prime potential where I have reached if I follow cathodic polarization. So, then I would see that case my I C triple prime is this one. Let us say this value becomes 10 to the power let us say it becomes 4. Okay. And this particular current density, of course, this is equal to I p, which is 1 ampere per centimeter square. So, now that case what would be the I applied? In that case the I applied was this much, but in this case I applied would be this much, which is would be equal to 10 to the power 4 minus 1 would be equal to 10 to the power 4 ampere per centimeter square. Now, if we follow cathodic polarization, I can reach to this E triple prime potential. That time the corrosion rate would be equal to the I A triple prime, which is at this particular location, and that will be the dissolution rate of that particular metal. But if we see the total current requirement for that circuit is 10 to the power 4 ampere per centimeter square, which is a very large current requirement. But here if we follow anodic polarization and if I reach E double prime potential, I see that the current requirement which is I applied would be only 1 ampere per centimeter square. So, that means in case of active passive metal, anodic protection becomes beneficial economically, because I need a much lesser current flow in the circuit for getting the same degree of protection. So, there it helps. So, this is the very concept of anodic protection, and this particular anodic protection is always applied for active passive metal. And here if you see that if we allow that particular metal to be in open circuit condition, the corrosion rate of course will be this. Okay. So, that means here you have to forcefully take the potential to E double prime, so that I could experience the reduction in corrosion rate because of the very interaction of that potential line, potential region, potential plane with the passive zone of that particular active passive metal. Now, if I try to see this, of course, in the beginning of the polarization I have to go through this I critical, that means the maximum current density. So, in the beginning of the process of anodic polarization, I do need a very high current flow, because if I see I critical, the total current density requirement would be this much, which is very large current density requirement, which becomes my I applied. So, in the beginning it will be very large current requirement, but once we cross that particular barrier of large current, then I will be needing a very small current in the circuit for getting a very good protection of that particular metal, and that happens because of the passive film formation on that particular metal at that potential, which is E double prime. So, this is the concept of anodic protection, and as well as the comparison with the cathodic protection. So, in case of active passive metal, it is always better to have anodic protection if of course we have a very cheap source of electricity. But if we try to follow the same protection in case of cathodic by doing cathodic protection in active passive metal, we will be needing supplying all the time very large current density. So, that way the cathodic protection becomes disadvantageous in case of active passive metal. So, this is about active passive metal, passivation and mixed potential theory interaction. So, we will not go further, but there could be many other things that can be talked about. For example, we have talked about that passive film or the passive region, we see transpassive zone, but there could be possibility that sometimes in the polarization graph you might find some hatches, some if I try to see the polarization graph, the experimental polarization where E versus log I is plotted, you might find a plot like this. So, those particular noises, they could be indicative of metastable peat formation. Okay. So, now those metastable peat might, one of those metastable peat can grow and form a stable peat, and then that stable peat keep on increasing with the increasing potential. So, there are techniques called potentiostatic technique, there are techniques called cyclic potential dynamic test, where you can sense where is that particular potential where I can start getting those metastable peat. Now, if I try to see this particular graph, the peat is growing and then finally it is failing, that particular metal passivation is breaking, and that is what you have a transpassive zone. There could be cyclic polarization, the cyclic polarization graph could be like this. So, that time this could be the point which is basically indicative of the repassivation potential. So, we are not getting into those complications. So, let us confine our discussion on the active passive metal and its interaction, and how with different cathodic reactions, and then whether we can analyze those data with the help of mixed potential theory. So, we have discussed corrosion events on the basis of mixed potential theory, and for that we have considered two aspects. One case is when the metal is active throughout, another case is when metal is active passive, and there are situations like the corrosion is controlled by activation processes at the metal surface. That means cathodic as well as anodic processes are all in the activation mode. That means that can be explained by Tafel equation. And in another situation where we have considered active metal and the cathodic process will be concentration controlled, and that we have seen in case of a metal corrosion when the velocity is changing. Then in case of active passive mode, we have considered in active passive as well as active metal, we have considered effect of galvanic coupling with a noble metal, and when we have galvanic coupling with a noble metal, the active metal corrosion increases as the I0, that means exchange current density of the cathodic reaction, increases on the noble metal surface. But in case of active passive metal, there could be a situation where because of the galvanic coupling with a noble metal, the metal can reach passivity, and that could be a case where we have considered in case of titanium platinum alloy, where titanium passivates because of galvanic coupling of titanium with platinum, but it may not be the same for a situation where iron is galvanically coupled to platinum, in a situation where iron also shows active passive transformation, but if it is coupled with platinum, that time the corrosion process will be all the time activation controlled, but it will not reach to the passive region. So, those are the typical considerations we had, and also we have understood from the active passive this mixed potential theory that the concept of cathodic as well as anodic protections. In case of cathodic protection, we have to go for this particular type of protection in two ways. One is impressed current cathodic protection, another one is sacrificial anode, but both the cases will be applicable to an active metal. But anodic protection, that means the metal can get protected if the polarization happens in anodic side, that time that kind of protection can be possible if the metal shows active passive transformation. Otherwise, it will not be possible to protect any metal anodically. Now, once we understand these things, only one small consideration will have, that is called linear polarization. And in case of linear polarization, we will talk about linear polarization. And once we consider this, then we will close our discussion on this corrosion, and then we will catch up with the high temperature oxidation. So, in case of linear polarization, if I see the Butler-Volmer equation, which is I equal to I 0 exponential alpha n f neta by R t minus exponential minus 1 minus alpha n f neta by R t. If we see this equation, where of course alpha is a symmetry factor, n is the number of electrons involved in that reduction or oxidation process, F is 1 Faraday, R is universal gas constant, T the temperature, and eta is basically the over voltage. Now, if neta is very small, that case I can expand exponential alpha n f neta by R t and have approximation, because this can be expanded as 1 plus alpha n f neta by R t, whereas exponential minus 1 minus alpha n f neta by R t, it can be also expanded 1 minus n f neta by R t. In this is basically expansion. We know that exponential x can be written as 1 plus x minus plus x square by 2 factorial 2, x cube by factorial 3, like that. So, if we follow this, and if this x is very small, we can ignore the higher order term, and then we get these only the first two terms if we take, and then if we do approximation, then we will see that it will become 1 plus alpha n f neta by R t minus 1 minus alpha n f R t plus n f R t. So, all the term cancelled. So, finally, I get this I 0 R t. So, now this term, if we consider fixed temperature, pressure in F, R, even I 0, all are constant for a particular process, then I could see this I proportional to neta, and that means if I try to plot I versus neta, then I will get a straight line plot. So, this is possible if this is very small, fine. So, this is the concept we will be using in order to explain, or in order to get the relative corrosion tendency of two metals in a particular solution. So, we will take it up in our next lecture, this linear polarization part, and then try to understand the relative corrosion tendency of metal in an electrolyte, and in fact, we will be trying to understand the polarization resistance. So, let us stop here, we will continue our discussion on this linear polarization in our next lecture. Thank you.